Welcome back to the Student Hub Live. Glaciers on Mars, missions to Mercury and mapping Venus. We're going to find out what exciting research is happening at the Open University with members of the Planetary Environments Group. So I'm joined by three members of the Environments Group. Dave Rothery, Professor of Planetary Geosciences, who you may remember from our Wheel of Ologies quiz. And we have Frances Butcher, who is a third-year PhD student, and Chris Malliband, who is a second-year PhD student. Many people don't know that we've got PhD students at the Open University and doing such exciting things. So thank you for coming along and talking to us. So I'd be interested to find out about why each of you are interested in your planets. And our viewers can put questions to as well, which I'm sure they will. And HJ will be feeding those in from the hot desk. Dave, now, as I said before, some of our viewers will have recognised you from our Quizmaster, but you do a lot of other things as well. So Tell us a little bit about some of the modules and things you're involved with.
Well, my main thing at the moment is running S283, the Level 2 Planetary Science course. Brand new books, just published for the 18J presentation. It's a 30-credit course, which gives you choice of what speed to study or what to study it with. So I think it's really good from that point of view. Popular course because planets, as I hope we'll discuss tonight, are very interesting places. You learn about other planets, especially the rocky ones. That helps you understand the planet that we live on. But I'm a geologist originally. I wrote the topic 7 for S111, the topics in science, the first 60-point science course that you will do if you're going towards a science degree. I did a bit about plate tectonics and how that affects distribution of species across the globe. So that was quite fun, very multidisciplinary. And I run the Moons MOOC, which the OU runs in conjunction with FutureLearn, massive open online course, free learning about moons in general, not just our moon. Starting again a week on Monday. If anybody's got 3 hours a week over the next 8 weeks, want to spend having fun finding out about moons. A
very popular MOOC, and one that our students often recommend at Student Hub Live as an additional thing, perhaps because you keep plugging it, Dave. But we have a lot of students here in STEM, so 3/4 of our students at the moment watching, although others may not recognise some of our acronyms like WELS or FBL or other. So we've asked which subject you're studying. The choices are science, technology, engineering and maths. WELS is wellbeing, education and language and sport. Faculty of Business and Law is FBL, and other will be all the other things, predominantly things like arts and social sciences, etc. We've also asked about which level people studying. We've got a lot of students here studying at level 2 and 3. So obviously, Dave, you've been promoting the show tonight. We've also asked which way you draw the crescent moon. So take your time in voting. To vote on these interactive widgets, if you haven't done so already, just click on the icon that applies, press submit, and you can send. HJ, how's everything over there?
Well, it's going well. We're still thinking about whether we're going to go generalist or specialist, but Alice is a bit worried that she's going to be convinced to do another course by this session. So we'll see by the end. She'll let us know. And if you do the Moons MOOC, I'd love to hear how it goes as well.
I can't please just interject. Please do vote on how you would draw the crescent moon. There's a serious point I want to come back to at the end about that.
No, absolutely. I can't remember the right answer. Well, we'll find out, I'm sure. Now, Dave, in addition to running all of these modules and MOOCs, etc., you've also been doing some really interesting research.
Well, yes, I'm involved in BEPI Colombo, which is the European Space Agency's mission to Mercury, which is launching in October, maybe early November, to go to Mercury. And we'll go into orbit about Mercury with a whole host of instruments, one of which was built in the UK, designed at Leicester University. But Mercury is a fascinating planet. I've been involved in Mercury for 10 years or so now, and I've been using data from a NASA mission called Messenger, which orbited Mercury very successfully. It was the first probe ever to orbit Mercury. It was 2011 till 2015 in orbit, and it's the best database we have for Mercury. It's seen the whole planet. Not all of it very well, but we've got the whole planet. This is a globe of Mercury with images laid down on it, and we're trying to understand how it works. It's a really weird place. It's smaller than our planet. It's smaller than Mars. It's bigger than the Moon, but that makes it the smallest proper terrestrial planet. Yet it's very dense. It's got a very large core, so it's lost, we think, most of the rock it originally had. And yet the rock that's left is rich in volatile substances like sulfur and chlorine and sodium, which you don't expect to find on a body that close to the sun. So it's a place that doesn't stack up. It's volatile rich, and it's been involved in some horrendous event to strip it of most of its rock in a distant past. But since then, it's had an amazing history. And I have several students working on Mercury, one of which is Chris here, is mapping part of the planet to try and understand the context of the observations we will make when we get our own mission there, the Bepi Colombo mission.
So Bepi Colombo is a mapping mission because
Not just. Bepi Colombo is doing everything. It's got visible imaging, it's got infrared imaging, it's got, it'll map the topography with a LiDAR, a laser ranging system. It will map the composition in the thermal infrared, which has never been done before. It will study the magnetic field, it will study the particles around Mercury, it will study the density distributions inside Mercury. What have I missed out, Chris?
The magnetospheric orbiter, the JAXA contribution as well.
Yeah, we have two orbiters. There's a European one and a Japanese one flying together. They're bolted together and they separate once we get into orbit. And so the Japanese one will concentrate on the magnetic field because Mercury, strangely for a planet this size, has its own magnetic field.
Now, I want to talk specifically about the planets, but before we do, because for some students, they may not know how amazing actually the Open University's contribution to space exploration is, because you've mentioned lots of things here. So there are all of these various places basically that are inputting into certain missions, etc., with various things going on. Such and such is owned by such and such. You're looking at various instruments, various different measurements, etc., and you're all basically clubbing them together, aren't you, to have some sort of mission? I mean, that's incredibly complex.
Yeah, even NASA on a spacecraft has instruments built in several different institutes and contributed by other countries. In the European Space Agency, the Bepi Colombo instruments is one that's run by the UK or contributed by the UK. That's the X-ray spectrometer, which I didn't mention. Our own instrument will map the surface composition in X-rays. A very, very clever instrument. The Italians are running the camera system and the spectrometer. The Germans are doing the thermal infrared system. The laser system is Swiss. It's all different countries and many institutions from different countries. And here at the OU, we're contributing, we're designing camera systems which may go to the moons of Jupiter. We're designing geochemical analytical instruments that may go on a lunar lander called Prospect for mission, isn't it? The South Polar lander?
Yeah, I think Prospect, isn't it?
And we've got an instrument orbiting Mars at the moment.
ExoMars Trace Gas Orbiter.
The Trace Gas Orbiter. So to be involved in the game, you need really to have facilities to design and build space-hardy instrumentation, and you need the scientists who can work with the data. I'm more in the latter. I can't build instruments, but I have colleagues who can. There's a lot of teamwork between colleagues at the single place and between multiple institutions and between many countries.
And as well, the OU have contributed to other missions as well, so the surface science package on Huygens and Beagle 2. So it is not just something that the OU's recently started
Beagle
doing.
2 was constructed in this very room, actually.
Yes.
And people in the chat are talking about Rosetta also.
Yeah.
Of course, I missed that out.
That's important.
We designed instruments that orbited and in fact landed on a comet. Yep.
Incredible. Francis, what are you doing?
I'm studying the planet Mars, not Mercury, and I'm studying glaciers on Mars, which is a feature that a lot of people don't know exists. They think water doesn't exist on Mars, but it does in the form of ice. And so I'm studying these glaciers and trying to work out what they tell us about the environmental history of recent Mars, and if there may have been liquid water associated with them.
And what have you found? Because you're in your third year.
Yeah, I am, scarily. I've found that in very rare localised instances, glaciers on Mars have melted, and despite the fact that Mars' very recent climate has been extremely cold and extremely dry, and this is a period during which these glaciers formed only 100 million years ago or so, which is very recent. The climate's been very cold, and yet we've had small localised melt events, and so we think that may be driven by internal heat of the planet. For example, magma rising up within the crust. So it's possible that we've had very recent meltwater flowing across the surface of Mars. We've seen 2 locations where this may have happened. Now there's thousands of glaciers on Mars, so there's a lot more to explore. But yeah, it's been fun, and hopefully we'll find some more.
So how have you done this?
Well, I use planetary images, so ones taken from orbiters circling the planet. I also use 3D data that's also taken from those orbiters in amazing resolutions, in a lot of ways comparable to what we have on Earth. So we can see Mars' surface down to 25 centimetre resolution. Our 3D models can get down to 1 metre resolution, so we could effectively spot you sitting in that chair on Mars if we knew where to look. And that allows us to reconstruct the surface in incredible detail. People working on Earth are jealous of the data we have on Mars. So that helps us to look at these features in all their glory, map them and measure them just as you would on Earth, and also use numerical models, which are computer simulations, to work out what these glaciers might have been doing, simulate different environmental conditions, see what makes them melt according to theory. So yeah, lots of diverse ways we can do this. Of course, we can also go out into the field and see what we can learn from Earth, from glaciers on Earth, and things like that. So.
Excellent. Well, we've got an image, Frances, again, of some of these glaciers. It looks absolutely incredible. Tell us about this.
So this was an image that appeared a couple of weeks ago by Pete Grindrod at UCL in London, and it's basically a 3D model that's been generated just from 2 images taken from the Mars Reconnaissance Orbiter, and basically the camera looks in 2 slightly different directions, and that allows you to construct this 3D model. Now this is slightly vertically exaggerated. It's everything's about 2 times higher than it would be in real life. But this is a present-day glacier in the mid-latitudes of Mars, just descending through this valley, basically. This is actually a really interesting one because the small lobe you can see coming out of the valley seems to actually be encroaching on top of another glacier, which is at the bottom. We can see from these very pitted textures that this is probably very ice-rich material. So it looks like this younger glacier has descended down this valley. You can see its flow lines, those long linear features, and you can see its lobe is where it's terminating, but there's another glacier that continues out from underneath it. Now, the ice in those glaciers isn't actually exposed at the surface. It's covered in probably a few metres, if not tens of metres, of dust and debris, which is how it's allowed to be stable. The only surface ice we see is in the polar caps, which is why they're bright white, and nowhere else is bright white, like a normal glacier. But we have glaciers like that on Earth as well. In the Himalayas, in parts of Antarctica, you have pure water ice glaciers that are just covered in debris, which protects them from the environment. So
using a lot of these images, you're looking at things that we know about and measuring changes and making them predictions and models.
Mm-hmm. Not so much changes. We can't really see changes in the glaciers at the moment because it's so cold at the moment that they're probably not moving. And if they are, our images aren't separated in enough time to see distinct changes. There are people looking, and hopefully we might see something, but so far we haven't.
We can see landslides and dust storms on Mars and changes around the fringes of the polar caps, can't we?
Yeah,
but it's just that the
avalanche.
glaciers aren't changing at a rate to see.
Well, Davin wants to know if you found any caramel in the middle of Mars. Do you get that all the time?
I've never had that question. We actually, for the first time this year, we've got a lander that's going to go and for the first time have a dedicated study of the interior of Mars. It's the NASA InSight mission. And it's kind of the first opportunity we've really had to look beneath the surface of Mars. We have ground-penetrating radars that help us to look through the ice and the upper surface, but the InSight mission is going to go and put a probe down into the surface. It's going to search for seismic activity, measure the internal temperature of Mars, and this is really going to give us the first insight that we have, hence it's called InSight, as to what's going on inside the planet. And this may completely change what we think, or we might have been right all along as to what's inside Mars, but we really don't know, to be honest.
Well, how exciting. But I think, Davin, you shouldn't brace yourself for the caramel. It's very unlikely. But how exciting. We've had other questions about areas of Mercury that have never seen the sun, and is there such a thing? Chris, can you tell us about what you're doing? Because you're also making geological maps as parts of Mercury, and also you're trying to work out some of the history of the plains formations.
Yes, yeah. So my PhD, one of my supervisors is Dave, and I am making maps of some of the some parts of Mercury. So I think we've got a couple of images that sort of show roughly what I do on a day-to-day basis.
Right, let's take a look, and you can talk us through some of these images.
I can try and talk you through some of them,
So these are Malliband 1, 2 and 3, aren't they?
There we go. Ignore the list of lines and pick colours at the side. So this is what I spend most of my day looking at. So this is a patch of the area of Mercury that I'm making maps of. And so this is some of the photography that we get from, the imagery we get from NASA's Messenger mission, which Dave was talking about earlier. And this is the best imagery we've got until Bepi Colombo arrives. So we've both got the normal pictures like that in various shades of grey. And then we've got another picture as well, which shows what it looks like in a bit more colour. This is an enhanced colour picture. So this is, if you had supervision and you could sort of, if your eyes were attuned just for what the grey of Mercury and you stretched it out and could see the full range of colours within that.
I just have to ask, just looking at the side, I told you told us not to, but is Hummocky crater a technical term?
It is a technical term, yes.
We get a lot of interesting descriptions in planetary geomorphology.
Wow.
So yeah, there's the hummocky textures. We've got, it just means, because most of the craters, the floors on Mercury have got this really very smooth there. When the crater hit, it caused a little bit of the rock to melt, and that sort of causes a lot of smoothing of the bottom of the crater. In some of the older craters, or slightly more unusual craters, you get this hummocky, because it looks like you've got little hummocks on it.
Oh, Alice says it's really, really beautiful. Let's look at the third image.
So this is what I try and make out of these pictures. So I try and draw around the craters, where the crater rims are, try and work out how old these craters are roughly. It's hard to put a date on them, but you can work out how degraded they are, how sad they look really, and then you can see where there's some where you've got much smoother areas, which is where we think lava flowed more recently, and so you're looking at more recent giant flows of lava. So that sort of pale pink bit is where we think there was quite a young lava flow, and that's actually one of the youngest areas of what we call plains on Mercury, and that Aparangi Planitia. And then we've got some older stuff, which is sort of the brown stuff, which is all got lots of bits of crater and things. It's all been much more smashed up and broken apart.
And the yellow stuff is the youngest impact craters on top of it. Chris is mapping 1/15 of the planet Mercury. That was just part of his map.
Oh, it's a little bit of that.
There's a student a year ahead of Chris mapping the area to the north, and a student a year behind Chris mapping the area to the south of Chris. And we have Italian colleagues mapping elsewhere on the planet. And I hope to start a new student next October to map another 15th of the planet. And by the time we get Bepi Colombo there, we'll have a complete series of the best geological maps we can get. And that will help us understand the context of the new data that comes back from Bepi Colombo.
And then you make them into a globe like this.
Yeah, we'd love a geological version.
Yeah, absolutely.
That would be your idea. But you say, this is what I spend my day doing. So you're both looking at a lot of things in a lot of detail. But I just wanted to ask what got you all, in fact, inspired in studying, doing this in the first place, because it sounds like the idea is so different from the reality, which is, minute detail mapping, etc.
Should I get, yeah. So I was hooked by astronomy and planets from a very, very early age. Before I could walk, my parents had me looking down telescopes. I think the first thing I ever saw down a telescope was Saturn, and it's still imprinted on my memory. But I grew up in the Lake District, and in the Lake District you not only have these amazing landscapes that have been affected by glaciation, but you also have no light pollution. You have these amazingly dark skies, and that meant that I was just taken aback by astronomy and the starry skies and stargazing every single night. And that meant that I was both fascinated by geology and geography and glaciology, and as well as astronomy. And so I thought, well, how can I combine these? These seem so disparate. And then it occurred to me, well, why don't you look at other planets and see what's going on there? And then I found out there were glaciers on Mars, and that was it. I was sold. And so that's what I look at. Of course, I do like to explore Earth as well. But the planets were where my heart was.
Oh, what about you, Chris?
So I was, as a much younger, I was very interested in geology. My family is from Scarborough originally, and so I was able to go fossil hunting along the beaches of North Yorkshire, which got me interested in rocks. And I was also typically, as a much younger person, interested in space, and I've always enjoyed space and rocks. And when I was at high school, I was actually involved in an OU outreach project, and I got to come to the OU Physical Sciences department and got to look round and see that you could do rocks and planets. And space rocks was grabbed me then, and it's never quite let go. So it's quite poetic actually that I've ended up doing my PhD here.
And are you also interested in Venus?
I am also quite interested in Venus. So I did my master's work on Venus, which is a much maligned and forgotten planet. Mercury is absolutely fascinating as well, but Venus is such a fascinating planet that we just know very little about in comparison. And we know a bit about Mercury, and we're going to get a fantastic suite of new data, which is going to revolutionise with Epic Colombo. But again, Venus has been a bit forgotten about. But there's some really interesting geology on Venus. Some things that we don't quite see anywhere else in the solar system. So we've got things like Corona, which I think we've got as a picture to show you.
Oh yes, let's take a look at some of these pictures.
Yeah.
Dave, we do have some questions on the hot desk, so we'll go to them in a second, but let's take a look at these images first.
So this is a type of feature that we find all over Venus, and we think we might possibly find a couple of them on Triton, which is a moon in the outer solar system, which I think you find out a lot more about in the Moon's MOOC, but we've not got a very good picture, so we're not quite so sure. But these are really strange features on the surface of Venus. So you see there's like a big ring.
How big's that?
So that's about the size of the US, that thing. It's the biggest one on Venus. You get really nice pictures of it. But we think these are sort of something to do with upwellings of magma possibly on Venus. And you've got these big faulted rings, and you often find lots of volcanoes in the middle of them. You don't always find volcanoes in the middle of them, and they've been linked to all sorts of weird and wonderful things. But we don't fully understand what's going on there, and it's one of the enigmas of Venus. And one of the other enigmas of Venus is the other picture I've got, which is of Tessera, which is really odd terrain that we find in patches all over Venus. And this is really old as far as we can tell, and it's all cut up and messed about. It's
broken up by faults in different directions at different times.
All over.
Is that still correct?
We think so, yes, okay. But it's don't try and start mapping out faults in those, or you'll never stop. It's like counting sheep at night. It's very good for putting you to sleep, trying to count the faults in that.
I can imagine. Gosh, let's take a quick trip to the hot desk before we come back and ask Dave how you got interested in this area. Dave.
Yeah, we've got loads of great questions, so knowing where to start is always an issue for me. But I think one great question that came up is, what's more likely to be found on Mars? Water under the surface or signs of life? Or will we just not know until we get there?
Well, Francis.
In terms of the likelihood, I wouldn't want to put a bet on it.
Go on.
we do have a lot of ice locked up in the surface of the planet, and it all depends on how much heat is being pumped out still from the inside of the planet, because effectively the thing that would be making it melt within the crust, which I think the question was, would be this heat from inside. And so I guess this is what the InSight mission might tell us more about, to tell us whether we have enough heat to do that. I wouldn't say it's completely unlikely. We'll see. There's certainly evidence that it's burst out.
Ice is water. It's the compound H2O. It's just frozen water, and there's frozen water in many places on Mars. Liquid water is not stable at the surface. That's the trouble.
Yeah.
And the implication then is about life, isn't it?
Mm-hmm. This is a question I get a lot.
Yeah.
So, obviously, the only place we know there is life at the moment is on Earth.
Could you show us on the globe where the past present ice is?
Yeah, sure, yeah. So, am I able to move this? Can you still see this? So, Mars is obviously the red planet as we think of it, but it does have enormous polar caps. So, up here, this white area is the North Polar Cap, and we've got another one down here, which is more dust covered, but there is still lots of ice exposed here. And these are they actually contain about the same amount of water ice as the Greenland ice sheet. Each of them has about the same amount. There's also some CO2 ice on the surface of the South Pole because it's so cold. The CO2, which is a predominant gas in the atmosphere, freezes down onto the surface. There's about 8 metres of CO2 ice on the surface of that. So that's the polar caps, and they're very thick, kilometres thick, so very similar to an ice sheet you might see on Earth. But effectively, the planet is icy all the way down to about these latitudes. So the equator is here, and the glaciers that I look at are in a consistent band all around these mid-latitudes, so about the same latitude as southern Europe on Earth. So glaciers in the Alps, kind of similar place. But then all between the poles and the mid-latitudes, you have massive blankets of dust and ice. We've very recently seen ice cliffs on Mars. So this is exposed ice within these blankets that's wasting back, and it's exposing ice at the surface. So there is a lot of ice. The mid-latitude glaciers alone contain about the same amount of ice as all glaciers on Earth, excluding the two main ice sheets. So ice on Mars is forgotten when people think about water on Mars.
And where is the glacier that you showed us earlier?
That glacier, oh, good question. I think that is in this region here called Flegramontes. I might be wrong. But it is one of my favourite ones. It's very distinctive. And this is actually an area that I study in a lot of detail. It's one of the locations where we found evidence for melting of glaciers. So that was a mid-latitude one.
I love this. This is my area, and Dave's got this workforce of people providing all these maps. It's incredible, and you're showing them for a while. People have been voting on our crescent moon. Dave, they want to know whether or not they can Google what the crescent moon would look like in the southern hemisphere, or whether they would get in trouble with you.
Well, no, that's exactly what I was getting at behind this question. I was watching Wallace and Gromit's Grand Day Out on Sunday night on iPlayer, and they looked through the window, having their evening cups, they looked through the window and they saw the moon. They saw a crescent, and it was the wrong way round, because Wallace and Gromit live in Lancashire, okay? And the crescent that they saw out of their window in the evening sky was like that. It's choice 2 on the...
Do you want to know what people were saying,
I've
Dave?
got it in front. Well, tell us.
They said 14 for choice 1, which is the smile-shaped moon.
Yeah.
48% choice 2, and 38% choice 3. None had the moustache-shaped choice 4.
Well, you would see choice 2 if you're in the northern hemisphere. If it was a waning crescent moon, you're up before dawn, it would look like that, because the sun has to be below left of the moon when it looks like choice 2. So it's below, and so it means it's about to rise from the northern hemisphere. The way you will see in the evening, when the moon is a crescent, in about 3 weeks' time, will be like choice 3. The sun will look like that in the evening sky, and the sun will be below the horizon in that direction from the northern hemisphere. If you're in New Zealand, it'll be the other way around. If you're on the equator, after the sun has set, the moon looks like this, or before moon rise, or before sunrise, when it's the opposite phase. You never see the moon like that, because that means the sun's above you in the sky. So you wouldn't be seeing the crescent moon with the sun just above it in the sky.
So everyone who voted is right.
I wanted to know how you would draw the moon. And if you see the moon in The Simpsons, or Wallace and Gromit, on many Islamic flags, on that logo of that film company of a little boy fishing on the crescent moon, it's almost always drawn like choice 2, but that's not the choice, that's not the way round that you normally see the moon if you live in the northern hemisphere. So it's really weird that people perceive or just draw it that way round. Doesn't matter whether you're left-handed or right-handed, you tend to go for that way round.
An icon, perhaps, influencing our perception then.
Maybe.
Who knows? OK, so Dave, you've also brought some images as well that I'd like to take a look at. Now, what did you want to talk about? OK,
well, this is just to show what a fascinating place Mercury is. So I've got a series of 4 images where we just zoom in. OK, this is exaggerated colour. Mercury is not this colourful. The orange patch in the middle is just over 1,500 kilometres across, so just over 1,000 miles across. It's the biggest impact basin on Mercury. It's called the Caloris Basin. And we know it's filled with, it's not completely filled to the rim, but its floor is covered with lavas, which are this orange colour, and surrounding it in blue there are other lava plains. And let's just go to the next picture and zoom further in. That's going in towards the bottom part of the basin there. And running the rugged terrain at the south there is the rim of the basin, and the orange or smoother area inside the basin is the lava-filled floor of the basin. And I'm going to go, don't move yet, but towards the upper left, maybe you can see, there's a crater which is very far from circular. It's been described as kidney-shaped in outline. So let's go into that next picture. It's not an exaggerated colour, but
Wow.
the dead centre of that, hopefully everybody can see, there's a hole in the ground which is not a circle. Crater to the left of it is a nice impact crater, circular. The crater in this kind of 10 o'clock position is a nice circular crater. This one in the middle of that colour anomaly is not circular. That is not a crater produced by an impact, because impacts give you circular craters. That hole in the ground was excavated volcanically by volcanic explosions. In fact, by a series of volcanic explosions. I think they started at the left-hand end, worked their way towards the top right and finished off in the dark bit in the middle. A whole series of explosions blasting stuff out. And that yellow deposit surrounding it, with the kind of diffuse outer edge, is the stuff blown out by the volcanic explosions. So, nice volcanic eruption. And why is that interesting on Mercury? Well, it shows you that Mercury has got something which will turn to gas when there's magma involved. Now, when a volcano erupts explosively on the Earth, the magma rises to the surface, it experiences less and less pressure as it gets towards the surface, and gases in solution come out from being dissolved in the magma and form bubbles and make it go bang if there's enough gas. What's happening here on Mercury is there's some gas phase coming out to drive the explosion, but we don't expect a planet like Mercury to be rich in volatile stuff that close to the Sun, especially if it's lost most of its rock in some horrendous collision to leave it with a thin, rocky outer part and a giant core. And we have other evidence of it being rich in volatiles. The X-ray spectrometer that Messenger carried showed sulfur everywhere on the surface, and it's got chlorine. It's rich in volatiles. So these volcanic explosions just show you that it's rich in volatiles. There's one more picture, I think, even closer in black and white. That's just the complexity of that vent, and you can see that the left-hand end of that vent structure is quite muted. It's got impact craters formed on it. As you go further towards the right, it's a fresher and younger looking surface. So there's a long history of volcanic explosions in that one crater. And we're finding these all over the globe.
Well, our audience think that's incredible. What are they planning to do with these images, HJ?
Well, a lot of us are thinking about getting posters made, maybe a few cool mouse mats so we can ponder over Mercury while we're studying. We do like to be generalist with our approach here in the chat, so a few of us are thinking about doing the moon smoke. I know Stuart, at the beginning, he was like, oh, should I do it? And then a few seconds in, he was like, yeah, I'm going to do it. But yeah, we're just so fascinated by pictures. I know a lot of people are saving them, but we are interested as well what type of jobs we can do if we take modules in moons and planets and astronomy as well. What type of things do you reckon we could end up doing?
Well, like any science degree, it shows that you can apply yourself, and like any OU degree, it shows you've got a lot of self-drive to study that hard over many years. I would find it hard to pretend that most OU science degrees equip you to be a practicing scientist, because we don't offer a lot of field work anymore in field-based subjects like geology, or a lot of real lab work. There's a lot of virtual laboratory work, which is good and is a way to earn some skills. But I would say if you want a scientific career after an OU science degree, try and go and do a master's somewhere. We've got a space science master's here with quite a lot of practical work, remote practical work largely built into it. So there are ways. I know I have somebody applying for my upcoming PhD who's done the OU space science master's. So you can make it through the OU route, but do try and get as much field and laboratory experience as you can, as well as just studying planets remotely. That's my best advice.
Lovely. And if you're interested, we've been talking about the MOOCs, but there's also a new BOC coming up on astronomy where you can experiment with a telescope.
Yeah.
Online telescope.
This is great because many professional astronomers don't visit their observatories anymore. They run the telescopes remotely. And we can do that. We have our own telescope on Tenerife.
Yeah.
Robotic telescope, and you can do projects with that.
Absolutely,
and
on Mount Tate,
you're telling me
isn't it?
that's in the badged open course. You can drive the remote telescope.
I think you can. It's incredible.
You
So
certainly
students can have a go at it.
in S282, the companion course to S283, the level 2 astronomy course, and at higher levels.
Well, it's like when we were talking about the library and I said, well, they don't have any books there. And you said, well, we don't have any planets in our department. It's all online, isn't it? Because you're using this material. We are out of time, but I just want to touch on Venus, and because we've been talking about various missions, and I just wanted to ask about the scope in terms of prospects for missions to Venus.
It's a perennial problem. A lot of missions to Venus get proposed, and particularly at NASA at the moment seem to keep getting knocked back. But there is a potential mission coming up soon, possibly, which is in selection at ESA, which is Envision, which is led by people from the UK as well. There's a lot of UK involvement with that, with Richard Gale at Imperial College London and Colin Wilson at Oxford, who are very big in trying to push for that.
This is radar mapping
So
of
this
the
is going to be
surface,
radar
yeah.
mapping of the surface.
It's covered in clouds. You can't see the surface really except by using radar.
Wow.
So it's quite an extreme place to take things. We've actually landed on Venus as well. A lot of people don't realise that the Soviets during the 1970s and 80s actually managed to land on the surface of Venus, which is quite fascinating, quite fantastic really, because it's incredibly hot. It's one of the hottest planetary surface in the solar system. It's hundreds of degrees, and it's got a lot of extreme pressure because it's got a big, thick atmosphere. So there's a lot. It's really difficult to land there, and it managed to take a few pictures. But if we went again now, we'd get much better pictures, and we could have much better radar.
Because the technology is developing.
The technology has come on so
The
much.
Soviets had valves, I think, inside their spacecraft. We would build modern solid-state electronics which can't operate at high temperatures. You get to the surface of Venus at 500 or 600 degrees centigrade, 500 anyway, and you've got nowhere to dump the heat. You're not in space. You're surrounded by this thick atmosphere. You cook. So a spacecraft on the surface of Venus is very, very challenging because it's got no way to keep cool enough for the electronics to work. So landing on the surface, it's got a thick atmosphere. You can have a parachute and land gently, but once you're there, you cook very, very quickly.
It's such a challenging place to work on the surface. So it would be so again trying to get the money to send something to orbit, and we could go orders of magnitude better pictures. We could almost get as good as the Martians nowadays.
Balloons have been discussed. If you get something into the atmosphere that has a deployable balloon, it can float high enough in the atmosphere that it's not too hot, but below the thick clouds so it can see the surface clearly. And just by changing the buoyancy, you can rise and fall and pop down to the surface for a little while, sample it, and then just inflate your balloon and float up into the cooler skies for a bit. So it's pie in the sky at the moment, but one day we'll probably explore Venus like that.
And it's becoming more and more important to explore places like Venus because of all the discoveries we're making of exoplanets. And the Earth and Venus were made of similar stuff, and it would be trying to work out if we could tell the difference from so far away, if we've got a Venus or we've got an Earth. And if you're going to try and find somewhere that's habitable, you want Earth, which has got nice liquid water and all the things that we need for life to thrive. And Venus is sort of like a hot wasteland hellscape. And again, it could have had water. We think there might have been a surface ocean on Venus a long, long time ago, which has all been lost now. So there's lots of fascinating questions about our own origin that are linked to looking at Venus, and again looking at other planets like Mercury and Mars. We can't really understand the planet we're standing on unless we start to look at all the others that we've got, all our other laboratories to look at.
Well, thank you so much for that. We shall invite you back to find out more. So, Dave, Chris and Francis, thank you so much for coming along. If you're interested in finding out more about the various complexities, we did a whole feature on ExoMars looking at the various issues of getting up there, landing, etc., building instruments, and all of these various challenges that happen in what I imagine is incredible planning meetings and working together within these various international communities. And we've also got a lot of things as well from space science that you can look at on the Student Hub Live archive. We've got a YouTube channel that you can subscribe to and search for content on, and also you can look at the catch-up on the Student Hub Live website, which is studenthub.live.open.ac.uk. That is the end of the show, I'm afraid, but we have a lot more in store for you. We're coming back in March when we have 2 events. We've got a special event with classics. We're also having an event with the Faculty of Arts and Social Sciences to discuss Brexit, a very popular topic for conversation, and of course a lot more study skills and advice. So do keep an eye out for events on that Student Hub Live website. You can tell us what you've thought of the show, give us any ideas or suggestions or things that you might like to see featured in content by filling in the feedback form. That's on the website, a very short little simple form that you can just tell us what you thought was good or what you'd like us to improve on. And you can email us at studenthub@open.ac.uk, again with any thoughts, comments, and we will get back to you. HJ, you've been absolutely fabulous staying here for these 2 days. You can go home now.
I think I want to stay and watch all the catch-up. But I have to pick up on Stuart's points because it's always back to food. He says Venus would be a great place for a pizza oven. So I'm not sure whether the European Space Agency will be up for trying that, but we can certainly ask them.
The Italians would.
But we've had a great time chatting. I found out we're on the fence about being generalists or specialists, and we definitely know how to look after ourselves during our studies. And I'm excited to find out whether there is caramel at the centre of Mars. But it's been great chatting to everyone. If you're new and just joined us, hopefully we'll see you again soon. And if you've joined us before and been sharing your study tips, it's been fantastic as always chatting to you. So hopefully I'll see everyone at the next event if I don't eat too much food and struggle to get into here.
And there are still questions coming in. Yasmin wants to know about the polar magnetic flip. But email us, Yasmin, and we will find an answer for you. But we don't have time to talk anymore, much as I would love to. So I'd like to say thank you to all our guests. Thank you to you at home for talking, for sharing your ideas and advice. I hope you've enjoyed the programme, in particular the debate that we've just had this evening, which I think is on everyone's minds right now. There's plenty to watch on Catch Up. Do keep talking to each other. Enjoy your studies. This is such a wonderful experience. And I hope that you can connect with other Open University students in the various ways that we've been talking about and which you can read about on the website. The resources there show you about the Open University Students Association and all the various groups that you can join. That's all from us today at the Student Hub Live, but I hope to see you back in March very soon. Thank you for watching and bye for now.